everyone. So now that we feel a little more comfortable factoring using the GCF, today we're going to be looking at factoring the difference of perfect squares. Before we do that, let's refresh on what a perfect square is. The definition of a perfect square is the product of two equal factors, remembering that the word product means multiplication. So here's a table. All the numbers that are in bold are perfect squares. This is saying 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 16, and so on. This list will continue and continue and continue. Just remember that it is the product of two equal numbers. So like we said before, 3 times 3 is 9, 12 times 12 is 144. So it's only these numbers that are in bold that are our perfect squares. Now, we didn't use the word numbers in this definition because we also look at variables in algebra. So a variable, hopefully you notice here we have x squared, x to the fourth, to the sixth, to the eighth, to the 10th. It's going to keep going. All of these exponents are even. So if it has an even exponent, that makes it a perfect square. And the reason why is because x times x, those have exponents of 1. You would add those together, you get x squared. That's why x squared is a perfect square, because it's x times x. Same thing, I'm going to just do this over here. X squared times x squared. A number times itself, a factor times itself. You add those exponents, you get x to the fourth. So x to the sixth is the same as x to the third times x to the third, x to the fourth times x to the fourth, and so on. So if it has an even exponent, to find the square root of that, you would just take that exponent and divide it by 2, and we'll take a look at that. Okay, so another definition that we're going to be using today is conjugate binomial pairs. So a conjugate binomial pair is a pair of binomials with identical terms but sharing opposite operations in the middle. When factoring the difference of perfect squares, the result will be a conjugate pair. Example, here we have a squared minus b squared. That is a difference of two perfect squares. Notice we use the word difference here because we have a subtraction symbol. If there was a plus sign here, what we were talking about today would not apply. It can only be the difference of two perfect squares. Now we know that these are perfect squares because we're taking a and squaring it, b and squaring it. So no matter what that number is, it would be a perfect square because you would be squaring it. When we factor the difference of perfect squares, we end up with a conjugate pair like this. So it would be a plus b, a minus b. We have identical terms, but opposite signs. Also, you'll see that the square root of a squared is a, the square root of b squared is b, and we'll do a couple examples where you work with numbers so that becomes a little more clear. But it should always be a conjugate pair. If you have two sets of binomials where both have a plus sign, both have a minus sign, you did something wrong. Okay, so let's actually start factoring the difference of perfect squares. So it says factor the following expression, x squared minus 36. One, I have to be sure that this is the difference of perfect squares. I see that there's a subtraction sign, perfect. I know that this is a variable with an even exponent, perfect. And I know that 36 is a perfect square, awesome. So this is the difference of perfect squares, so we are able to factor it the way using the method we're about to do. So the first step when doing this is to factor out the GCF if applicable. That's always going to be your first step whenever you're factoring anything. Find the GCF. Sometimes it won't have a GCF, and that's fine, but you always want to be on the lookout first. So in this case, we do not have a GCF, so we're going to skip that step, but it is a very important step for other examples. Okay, 2, find the square root of the first term and place it in the first set of parentheses. So like we said in the last slide, when we factor this, we know that we're going to get two sets of parentheses. So the first thing I'm going to do is I'm going to make my two sets of parentheses, and I'm going to put them right down here. Okay, so the first step is find the square root of the first term. So I'm going to find the square root of x squared. And like I said before, you take that exponent and just divide it by 2. So 2 divided by 2 would be 1. So this is just x to the first power, and we don't need to write to the first power. That's what's going to go first in both sets of parentheses. So that's the first step. We found the square root of x squared. Second step, find the square root of the second term. That's what's going to go second in the set of parentheses. So we are going to find the square root of 36. What number times itself gives us 36? The answer to that is 6. So it's really helpful to remember what those perfect squares are and the square roots of them. That's going to go second in both sets of parentheses. And like we said in the last slide, we're going to make this a conjugate pair. So we're going to give one a plus sign and one a minus sign. And that is how we factor the difference of perfect squares. We find the square root of the first term, put it first in both sets of parentheses. Square root of the second term, put that second in both sets of parentheses. Give one a plus, give one a minus, and we're done. We can easily check this by using the box method or FOIL or the double distribution method. Either way, when we multiply this out, we would end up with x squared minus 36. Let's take a look at a couple more examples so you get a little more comfortable. So factor the following completely. Same thing, we have subtraction sign and we have two perfect squares. Here you're going to notice we have a number in front of a variable. That's fine. They're both perfect squares, so we're able to do this. So the first thing I'm going to do is make my set of parentheses. And we're going to find the square root of the first term. And I'm going to put it all together, this 9x squared. Now the square root of 9, what number times itself gives us 9, is 3. And like we just saw on the last slide, the square root of x squared is x. So the square root of that entire term is 3x. And a way to just check that, I'll do that right over here. 3x times 3x. 3 times 3 is 9. And then we add those exponents, so we would get 9x squared. So we know that that is the square root of that term. I wanted to just show you how we could check that if you get confused. Okay, so that 3x is going to go first in both sets of our parentheses. Now I'm going to square root 1 because that's our second term. The square root of 1 is just 1. 1 times 1 is 1. That's going to go second in both sets of parentheses, and we're going to give 1 a plus, 1 a minus, creating that conjugate pair. Okay, square root of the first term, square root of the second term. Let's take a look at one more. 49y to the fourth minus 25. We see all perfect squares. This is a perfect square. We have an even exponent and a perfect square here, and we have a minus sign, so we know we're able to factor this the way that it is. I'm going to create my two sets of parentheses. Square root of 49y to the fourth. The square root of 49 is 7. 7 times 7 gives us 49. And the square root of y to the fourth, take that 4, divide it by 2, and we get y to the second. That's what's going to go first in both sets of parentheses. And now let's square root 25. What number times itself gives us 25? The answer to that is 5. 5 goes second in both sets of parentheses. Give one a plus, give one a minus, and you're done. You can always check your work by doing the box method or double distribution. Either way, it's going to be the same process for every one. Find the square root of the first term, square root of the second term, put it in your parentheses. One gets a plus, one gets a minus. Good luck.